العالمين.
But we can also now use today's primitives to better explain some things that we've been asking you to take for granted over the past several weeks. So for instance, let me propose that we do one volunteer up here if we could. Could we get one volunteer who's just, you want to come straight up? Yep, right in the middle. Come on. You'll have to take a left or a right there. All right, so we have 2 empty glasses here and 2 colors of liquid. And we have, let me give you the mic, if you'd like to say hello to the group.
Hello, I'm Moeen. I'm in Thayer and first year.
All right, welcome. Well, welcome here. I'm going to go ahead and fill these 2 glasses with this colored liquid, purple here on my right. Let's fill up a glass here. Yes, don't drink. And now we'll put some orange in here. And what we'd like you to do for the audience, if you don't mind, is swap the 2 values. We've got a purple value and an orange value, and I'd like the purple liquid in this glass and the orange liquid in that glass, please.
Can I have another glass?
Oh, OK, good intuition, but for the microphone.
Can I have another glass?
So you can, and just in fact, I brought one here for you. Why are you asking for this, though?
Because if I just pour this into this, then it'll get mixed up.
Right, so obviously we need like a temporary variable, if you will. So here's your temporary variable.
And you want, OK.
Yeah, All right, so pouring the value of the orange glass into this temporary variable, if you will. All right, and now pouring the value of the purple glass into the former orange glass. And now the temporary value goes back into the original purple glass. And now I think we give you a round of applause for having done that very well. Thank you. All right, so it should go without saying that in the real world, like that's how you do this. And in fact, in code, that's pretty much how you have to do this. Although, ask us sometime for a super fancy way of doing it without a temporary variable. Turns out that is possible using bits. But for now, let's suppose that indeed this demonstrates what is the reality in code. If you want to swap 2 values, you need to have something like a temporary variable. So for instance, on the screen here is the beginning of a function called swap, whose purpose in life is to, as you just did, swap 2 values, call it A and B. So orange and purple, respectively, are now just A and B in integers to keep things simple. Well, here is the corresponding code, if I may, to what you just enacted as a human. You declared a temporary variable, called temp in this case, which was like me handing you the empty glass, and you stored the orange liquid in it, aka A. You then changed the value of the formerly orange glass to be equal to the purple by pouring one into the other, and then you did the opposite there. Now at the end of this, you still have a temporary variable that's now empty, so it's temporary in literally that sense. Like you just don't need it anymore, but it was necessary along the way. So I dare say this code is correct logically. Like this will swap 2 values, A and B, thanks to the use of that temporary variable. Unfortunately, though, if I actually do this in practice, let me go over to VS Code here and open a program I wrote in advance called swap.c, which does this as follows. In here, notice I have my prototype for a swap function at the very top. And let me scroll down to the very bottom. There's that exact same code. So I'm the same code for swapping 2 values, A and B, which I'm claiming for now is correct. Now, if I go back up here, what is main going to do for us? Main is really just meant to be a demonstration of the correctness of your algorithm. So here I declare on line 7 and 8 2 variables, x and y, being 1 and 2 arbitrarily, respectively. I then on line 10 just print out what the value of x is and y is, just so I can see it on the screen. I then call the swap function on line 11, and then I literally print the exact same thing again. I print x and y. Hopefully, it'll obviously be the opposite. So I think logically swap is indeed correct. Let me do make swap and then /swap, and I should see x is 1, y is 2, and then hopefully x is 2, y is 1. Enter. But I don't. And it did work in the sense that the code compiled, the code ran, so it's not like some bug in that sense. But because I don't quite understand what's going on underneath the hood, at least as of right now or prior weeks, this code here is indeed buggy in some way. But does anyone have an intuition, perhaps based on today's discussion, as to like why this code, while logically correct, clearly works in reality, apparently does not work in C? Any intuition? Yeah. Perfect. And to summarize, here's that term of art I promised. When you call a function and pass in two arguments, like a and b, you're passing those arguments by value. So copies of those values effectively. And so when swap is actually called here, when you pass in x and y, we call them a and b, but that's just a convention. We could call the parameters anything we want. What a and b are indeed the values of x and y respectively, but copies of the values. So this code here is very successfully in VS Code 2 swapping the values of a and b. But as you note, because I'm passing them in by value, literally 1, literally 2, and not by another term of art, by reference, aka by their addresses, swap has no capability in C to go to those locations, swap the actual locations, just like we did successfully in reality. But I think we really have the syntax already for solving this if we consider that really this is just an issue of scope. And we've talked a bit about scope in the past, whereby scope refers to the context in which a variable lives. And generally, I've claimed that a variable exists between the most recent curly braces. And that's pretty much true for the swap function, because a and b, I now claim again, exist only in the context of these curly braces. They have no effect on main up top, which has different variables, x and y. But we can consider now what's really going on underneath the hood. And here's that same picture of memory as we've seen in the past. If we zoom in and see on these little black chips, this is a bunch of bytes of memory. If I create a grid out of it just to kind of highlight that we can address each of these bytes, throw away the plastic circuit board and focus only on those bytes, what's going on underneath the hood when functions are called in C, which you've been doing for weeks now? Well, this rectangle of memory, if we kind of abstract it away further, is generally broken up into different regions or segments, like I called them earlier, and different things get put in different parts of the computer's memory. And without getting too into the weeds, when you double click a program on your Mac or PC, or when you do /something on a Linux, you are loading your machine code into the computer's memory from the computer's hard drive. So all the zeros and ones that compose Microsoft Word or Chrome or whatever are loaded into the computer's memory or RAM. And by convention, it's put up top in the so-called machine code area. And that's how the CPU has access to them quickly at that. Below that are what are going to be our globals, so global variables, which we haven't used very much in C, but you can declare them outside of main at the very top of your files. If you have globals, they end up there as well, just FYI. And then there's this big chunk of memory that we saw Valgren mention indirectly earlier called the heap. And it's kind of like heap, literally, like it's a heap of memory that you can use as you see fit. And the heap is where malloc grabs memory from. So initially, there's nothing in the heap. It's just a big chunk of free space. Anytime you call malloc, malloc kind of carves out from the heap area more and more bytes. And malloc keeps track of essentially which bytes have already been allocated. So initially, it looks empty, but different bytes, squares, if you will, keep getting requested again and again as a program runs, thanks to functions like malloc. And it grows, if you will, conceptually down. So the more and more memory you request from malloc, it starts up here, but then the next chunk you get is down here conceptually. The next chunk is down here, down here. So it kind of fills the available space in the computer's overall memory. But there's this other chunk of memory called the stack. And just like a stack of trays in like Annenberg or a cafeteria kind of grow upward, so does the stack of memory. And it turns out the stack is where functions have variables and have arguments stored temporarily. So whenever you call a function and it has variables inside of it or has arguments there too, this is the chunk of memory in the computer's overall block of memory that are used for functions. But anytime you call malloc, it's memory up here. Right? At the end of the day, they just had to pick a direction, top, bottom, and technically it's an artist rendition. You could circle this thing around any orientation you want, but you're just using a finite amount of memory in this conventional way. Malloc starts here, functions start here. Now you can kind of see where like bad things can happen. And indeed, one of the other reasons computers can crash is if you ask for way too much memory from the heap by calling malloc many, many, many times, or if you call way too many functions, or accidentally, per last week, you recurse infinitely many times, you might have a segmentation fault. And that's because you're using too much stack memory. So this is bound to be a problem eventually. And the onus is on the programmer to just minimize the probability of doing that and really avoid the possibility of doing that by just checking return values, like checking if malloc or getString return null, because you can proactively with conditionals make sure that these two things do not collide by just making sure that you get back non-null values. So let's consider the stack in the context of swap and what's really happening here. And Carter, if you wouldn't mind helping me animate the screen here, when I call the main function of any program, it is allocated a slice of memory called a frame at the bottom of this stack. So if Carter, you want to go ahead and advance here, here's like the first slice of memory that will always be used by main, whether it has command line arguments or local variables. It just ends up here in memory. Suppose now, per our swap.c program, that main calls swap. Well, where does the memory for swap end up? Like right up here. So swap had two arguments, a and b, and it also had a temporary variable. So all of those end up in here in memory. And if you want to go ahead and advance again, Carter, once swap is done executing, whether it just returns because there's no more lines of code, or you explicitly return, this memory is just freed up automatically. You don't call free, you don't undo malloc. This just all happens automatically. It has been since week 1. Now, technically, it's still there, even though we've removed it from the picture. And there's your first hint of garbage values, right? Like there's still zeros and ones there, and they're left in the the previous configuration. And so the reason you get random values in the memory is because even though we haven't drawn swap here, there was stuff there a moment ago. It's going to be there the next time you use that same memory. Now, let's go ahead and step through this a little more methodically. Main has two variables called x and y, 1 and 2. So let's advance and represent x as 1, y is 2, taking up these two chunks of memory. When we call swap now, swap gets a new slice of memory that then gives us 3 variables, a and b, technically the arguments, and temp. So what happens? Well, because functions automatically pass in values by value, or rather pass in arguments by value, x gets copied into a, y gets copied into b, and then once we start executing the algorithm a la the watered glasses, well, what happens here? So if I execute the first line of code, temp equals a, temp gets a copy of a. What happens next? A equals b. So a takes on a copy of b, and now we do the final swap in the glasses, b equals temp, b gets a copy of temp. Now, we don't have to change temp because it's essentially empty, although there's the garbage value. 1 is always now going to be there until we reuse that memory. The important thing, though, is that a and b have been swapped. But what obviously has not been swapped, as is manifest as when swap returns, x and y are untouched because copies thereof were passed in. So we need a solution to this problem. And if we advance one more time, if you don't mind, let me step over here, but then call you back in a second. This code here is logically correct. This is what you did, but this is now a detail of C. You can't just swap the things by value because you're only changing it in the scope of the swap function. But I think if we change it to this and add some annoying syntax, we can solve the problem. Just like you can declare variables as storing addresses, you can declare arguments to functions, aka parameters, as taking addresses. This new version of swap means that a shall be the address of an integer. B shall be the address of an integer. And now it gets a little cryptic here. Temp is the same because it's just an integer like it was in week 1. Nothing special about temp. But if you want to get the value at a, you do star a. And that goes to the address, grabs the number 1, presumably. If you want to change the value of a, you go to that address, you follow the treasure map to the other mailbox, and you set it equal to whatever's at the value of b. You go to b as well. Last line, you go to b now and change it to be whatever the temporary variable was, which happened to be the same as a. So that's where the final value gets swapped. But here, there's a lot more like crisscrossing metaphorically across the stage where you're going to all of these different addresses in the swap function to make these changes. So if we advance now to the pictorial version of this, here's the same story as before with main. And x and y are 1 and 2 respectively. When swap gets called now, notice, and I'll do it with arrows here, a is effectively pointing to x, b is effectively pointing to y. If we really get into the weeds, these are actually like addresses, but who cares about the specifics? It's really just the concept here. So now what happens? Int temp gets star a. Star a means start at a and go there. Follow the arrow, if you will, sort of chutes and ladders style. And then that's 1, so we put 1 in temp. All right, star a equals star b. So let's do it from right to left. Star b means follow the arrow. It's 2. And then what do? Follow the arrow. It's now 2 because you copy 1 to the other from right to left. And then lastly, star b gets temp. So start at b, go to b, and now store whatever the value is in temp. So just by having this basic new syntax of like ampersands and stars and so forth, we can actually now go to places and circumvent what is otherwise a feature of C, that these variables are locally scoped, but you can still access things in other functions as well. So thank you so much for helping step through this. So we now have an application of this that explains why now in this version of the C code, this would actually now work. So in fact, let me go back to my swap code here. And let me change the function ever so slightly in VS Code. So let me scroll down leaving main the same, and let me change swap's prototype to taking in addresses. Let me go to A here, let me go to A here, let me go to B here, and let me go to B here as well. But nothing else changes. This change here in particular is enough of a clue to see that means when you call swap and pass in two values, I'm expecting addresses now, not integers. But now that I've made this change, I do need to go up to main and make one change. Does anyone have the intuition for what now needs change in main so that I pass in x and y by reference, that is by address rather than by value or copy? One second. Any intuition for what needs to change in main? Oh, yeah, in back. So close. So on the swap line, it's not star that I want in front of the x and the y. It's instead, what's the other one? It's the ampersand. Why? Because if I want to enable swap to go somewhere, just like Carter and I played this game with the mailboxes, I need to inform swap of the address of x and the address of y. And again, per the beginning of today's class, ampersand is the syntax via which we do that. So I add an ampersand here to get the address of x, ampersand here to get the address of y. And now this code lines up with the picture that Carter just helped us walk through. And so when I run make swap here, I have a mistake. Oh, what did I do wrong? Not intentional, but I guess worth pointing out. I screwed up here. It doesn't like ampersand x because of something on line 3, which is way early in the code. What did I screw up? Yeah, in the middle? Yeah, so this is why you should not copy paste, even though it's necessary for things like function prototypes. If I change swap at the bottom, I need to change its prototype. So let me add the star there, or just recopy paste it at the top of the file. Now let me do make swap again. Let me now do /swap, and I should now see x is 1, y is 2, and hopefully x is 2, y is 1, which I now do. So the logic is the same, the algorithm is the same, all the week 0 stuff is the same, except now in week 4, you just have a bit more expressiveness via which you can tell the computer exactly what you want to manipulate and how. Any questions then on this technique here? No? All right. Well, when we fix this, there's still going to be problems. And just so you've seen some terms of art here, this is bad whenever you have two arrows pointing at one another. Certainly if you might use and reuse more and more memory. And it turns out there's some terms of art that might suddenly now make sense, especially if you've programmed before. Bad things can happen by this design, but there's really only this kind of design because it's a finite amount of memory. So at some point, bad things are going to happen no matter what if a computer runs out of memory. So it's not that this was a poor decision. It's just sort of a necessary one given finite amounts of memory in a computer.